Hello everyone, and we're Team InDepth Engineering, and we're going to be presenting our progress on the BAMS project, or the Biometric AI Measurement System. Thank you to our technical directors, Bill Matuzak, Vice President at InDepth Engineering, and David Helms, a Senior Software Engineer at InDepth Engineering. Our team is made up of Whitney Schollerman, a computer engineering major, Cheng Tao Yu, a computer engineering major, and myself, Noah Nicolella, an electrical engineering major. InDepth Engineering is a company providing combat system software solutions to the United States Navy. InDepth Engineering has small business innovative research contracts in the following areas: adaptive training, artificial intelligence and machine learning, signal processing, spatial data visualization, and aquatic life detection, among others. The proliferation of wearable smart devices has led to an explosion of biometric monitoring and analysis applications. InDepth Engineering is investigating whether information from biometric devices can be used to optimize the performance of computer-based information system, or CBIS, operators. Motivation for this project is, with the age of data abundance, collecting large quantities of diverse data can be leveraged and used to search for hidden patterns in said data. If you can notice these hidden patterns, you can exploit that to provide further insights not normally seen by traditional forms of data analysis. A couple examples of these would be user authentication, that's based solely on mouse movements, and you can analyze whether or not a user is online or away from the computer solely based on recent gestures at the computer or things like that. In addition, there has been an explosion in biometric device usage. So stuff like Fitbit, as used in this project, among others like the Apple Watch and competitors in the Android market. The idea is that you might be able to leverage that data to optimize the performance of CBIS, or computer-based information system operators. This could help organizations like the Federal Aviation Administration, or the FAA, or the U.S. military, or even power plants optimize performance of their operators. The anticipated best outcome of this project is a system that can measure the relationship between CBIS operators' biometrics and their performance. So there's two major parts to this: the data collection phase and the machine learning model training part. The data collection portion involves developing a BAMS prototype that collects biometric and performance data. We use video games as the analog for sensor operation to collect and measure performance data, and a biometric data collection system such as a fitness tracker like a Fitbit or a head tracker, etc. The machine learning model training section of the project will be developing and training an AI model to classify this performance data based on in-game interactions and predict this performance based on biometric data. This is the performance optimization section of the project. RABO was achieved. RABO was to create a proof of concept for the BAMS project, and we have completed that. Despite not actually creating the model ourselves, we have proved that a model can be trained using the data that we have collected. So future teams will be able to design and implement a model to predict user performance from incoming biometric data. The team's key technical accomplishments include designing hardware and software system to record biometric and performance data, designing and implementing a set of scripts to process and interpret incoming biometric and performance data, and creating correlation heat maps and charts proving the relationship between scoring data and biometric data. The economic impact of this project is going to be a foundation for future company research into this field of study. By discovering these correlations between biometric data and performance data, we hope that InDepth Engineering will be able to further leverage these discoveries into creating a product for one of their many customers. In addition, this sort of research provides InDepth Engineering a competitive advantage in this field. The field of biometric data acquisition is only growing, and this research will give InDepth Engineering a foothold in that field. Here's a block diagram going over our broad overview of our data collection and machine learning apparatus. So the individual contributions of myself, Noah Nicolella, include setting up the head tracking monitoring system and the filtering system. I wrote a series of scripts to process data and generate inputs for TensorFlow and Python. I wrote a mouse tracker and keylogger to provide additional mouse and key press data. I troubleshooted and debugged data processing scripts. I began creating a Jupyter Notebook environment to start training the model. And I wrote additional set of scripts for time series data and assisted in the creation of correlation matrices to prove correlation between data sets. And with that, I will introduce Whitney Charlerman to discuss her contributions to the project.
While working on this project, I had the opportunity to work with a variety of interesting topics and gain experience with multiple useful tools I was previously unfamiliar with. My team and I dedicated time to research, particularly in areas of machine learning and the methods and practices used to create clean, unbiased data sets which are required to develop and train an accurate, scalable machine learning model. I also investigated different biometric data and device options that could best suit the project's needs by providing a variety of data metrics that could be used to reveal patterns and correlations with performance data. Most of my efforts were focused on assembling and implementing an additional biometric sensor into our data collection system, which measures galvanic skin response, or GSR, retrieving data collected by our chosen fitness tracker, the Fitbit Inspire 3, troubleshooting and optimizing our data collection system to make sure the system was functional and that the data we were collecting was accurate, combining and cleaning the collected data from each sensor into data sets, which were then analyzed using software that revealed patterns and correlations between biometric and performance data, and creating thorough documentation for programs written, as well as a step-by-step tutorial guide with instructions on how to set up and implement our data collection system, so additional volunteers could also collect and process data for analysis. For this project, we used AIMLab, which is a free AIM training software to collect our performance data. But I was also able to develop a custom AIM trainer game that directly collects and stores mouse and performance data. This Python-based program could be further developed to increase control and customization of performance data in future applications. The data system we developed consists of a head tracker, which tracks changes in user head position and orientation, a mouse tracker, which records mouse position and movements, AIMLab to collect performance data in real time, such as score and accuracy. The system also includes a galvanic skin response, or GSR sensor, which is used to measure changes in skin conductivity, which has been proven to be indicative of changes in emotional states. This sensor detects and measures positive or negative shifts in the emotional state of a user. We believe this device would provide additional useful biometric data which could provide useful insights into an operator's stress levels and how that may influence their performance. Existing commercially available GSR sensors were expensive, but I was able to locate parts to assemble our own GSR sensors for a fraction of the cost. I was also able to assemble, program, and calibrate our sensors, but we noticed that they were initially very sensitive. Minor movements due to the attached finger electrodes and outside vibrations were interfering with the sensor's readings. To fix this, Noah helped design a 3D printed case, which I was able to insulate with foam to stabilize the main sensor board component, as shown in the upper left image. The Fitbit Inspire 3 was the fitness tracker we chose for this project. Not only did it offer us a variety of data to collect and work with, but it also offered a well-developed application programming interface, or API, with a lot of resources for developers. Fitbit's API allowed us to access specific data metrics we were interested in, such as heart rate, as well as specific timeframes and customizable levels of detail. To access Fitbit's data server, each user needed to set up an account and register for a personal application, which was required to interact with Fitbit's API. Each account then needed to set up open authorization by generating custom access tokens, which would allow us to securely access our Fitbit data. I used the Postman API platform to develop and test requests for data collected during specific time intervals, and then implement them into a Python program that would collect and translate data from Fitbit's database for a given date and time, and then store that data into a local file. Our system also implemented a program to screenshot real-time score and accuracy data from AIMLab's user interface every second during data collection sessions. I was able to help develop and troubleshoot a pre-trained Keras-based optical character recognition model, which reads and translates collected screenshots into numerical values before storing them into a data file. I also dedicated time to collecting biometric and performance data, which allowed me to help troubleshoot and optimize our data collection system at various stages of development. Once we were able to collect and store data related to users' biometrics and performance, we needed to combine the data from each part of the system into one dataset, and then make sure we cleaned the data by removing duplicates, sets with missing values, as well as outlier values resulting from time misalignments, sensor glitches, and OCR misreads. I was able to modify existing processing functions and develop new functions in a Python program to process, align, and clean our collected data before storing it into a dataset file. Once we were able to generate clean datasets, I was then able to import them into a data science platform named RapidMiner, which allowed us to use its visualization tools to create and analyze data correlation matrices. Shown here is a series of heat maps we were able to generate from different data collection sessions. Each heat map has a square representing the correlation between heart rate and score circled. A noticeable correlation between these values consistently showed up, which allowed us to conclude that there is likely a distinct correlation between user heart rate and their performance-based score. We also observed varying correlations between GSR, heart rate, head position, mouse movements, and score change. When testing different scenarios, such as tasks that had enemies that could deal damage, high correlations between GSR and heart rate in relation to accuracy were more prevalent. Unfortunately, we are very limited in the conclusions we could confidently make due to the limited amount of data we are able to generate. We'd need to vastly increase the amount of data, as well as diversity of the group of users generating that data, to properly determine which data correlations would be worth focusing on for machine learning model training. Next, Changtao will share his contributions to the project.
My technical contribution, as I described in previous slide. First, I give a suggestion of testing tools, which is AIMLab. As I said, it providing valuable data for us to analyze on, and I had to testing out all hardware and software for the test equipment. Also, as a quality control, I denied the possibility of using Tobio eye tracker on this project due to license issue. The license with full access require much more funding that beyond our reach above of this project. And as well, I generated many test sections in order to get valuable data for our machine learning to work. Without those data, our machine learning is just a program that does nothing. Also, I as a individual have to learn in machine learning. I mainly use Google Crash Course, but I also use lots of other sources. With all those information, I can provide more valuable data, and I can stand the process of how machine learning being generated. As this slide shows, is a bunch of useful data that I have produced through a test section. As you can see the image below, that's the score came out from AIMLab. As you may notify that each score have a different name with its own time and second, which means those are time-sensitive data, which is very useful in TCN machine learning model, and we can use those data to find out the changing of the score and lots of interesting with the scores. Also, on the right hand of the screen, they are my mouse tracker data. They're not only recording the current mouse location, it also records how fast the delta movement, which is move of the mouse in X and Y location per second, which those reflect how fast I move, how well I am when I playing this testing data section. And also, As this slide shows, below is a quick snap of when I running all program for data collecting. As you can see, there are 5 files being created and there are 5 program has to be running simultaneously when I taking the data, which is very messy, and this is the most hardest part for a machine learning to work, in my point of review. Thanks, and proceed to next slide.
Using the proof of concept we created and the data we collected, a future team of Capstone students or company engineers will be able to produce a complete model that predicts operator performance. We'd like to thank the InDepth engineering technical directors Bill Matuzak and David Helms. We'd also like to thank the additional InDepth engineering members, John Vernaglia, Fran Zilstra, and Gregory Werner. We'd also like to thank the ELECOMP Capstone director, Dr. Harish R.D. Sunak, and the University of Rhode Island College of Engineering. Thank you for watching.